The exponential function e to the x. The definition of the number e. Recall that for x greater than 1, the natural log of x is the area under the graph of y equals 1 over x between 1 and x. The area of the green shaded region here is equal to the natural log of 2. Now notice that this blue rectangle has width 1 and height 1, so its area is 1. The green region under the curve is smaller than that, so we know that the natural log of 2 is less than 1. Now let's look at the region under the curve between 1 and 4. Its area equals the natural log of 4. Compare that to these three rectangles. Their areas are 1/2, 1/3, and 1/4, which total to 13/12. So we observe that the natural log of 4 is greater than 13/12 and therefore greater than 1. From this, we conclude that there is a number x between 1 and 4 where the natural log of x is equal to 1. We'll name that number e. That is, the number e is defined by the equation natural log of e equals 1. The inverse of the natural log function. Since it's always increasing, the natural log function is 1 to 1. That is, each number y in its range corresponds to exactly one number in its domain. Therefore, it has an inverse, which we'll call for the moment inverse natural log, which is defined as follows. Inverse natural log of x equals y is equivalent to natural log of y equals x. Recall that the graph of the inverse of a function f is the reflection about the line y equals x of the graph of f. So the graph of inverse natural log looks like this. By definition, the natural log of e equals 1, so the point e, 1 is on the graph of y equals natural log of x. That fact is equivalent to inverse natural log of 1 equals e, and the point 1, e is on the graph of inverse natural log. Also, we know that the natural log of 1 is 0, so inverse natural log of 0 equals 1. The natural log of e to the x is equal to x times the natural log of e by a property of the natural logarithm. But the natural log of e equals 1, so the natural log of e to the x is equal to x for all x. That equation is equivalent to inverse natural log of x equals e to the x for all x. So we now have a simple explicit formula for inverse natural log of x. It's the number e raised to the x power. So the result here is that the exponential function e to the x is the inverse of the natural log function, and vice versa. In other words, e to the natural log of x is equal to x for all positive x, that's the domain of the natural log function, and the natural log of e to the x equals x for all x, which is the domain of the exponential function e to the x. In still other words, the natural log function is nothing but the base e logarithm. Now, since we know how to differentiate the natural log of x, we can also differentiate its inverse e to the x. Let's first approach this geometrically. Here are the graphs of the natural log of x and e to the x. Suppose that s is a positive number on the x-axis. There is a corresponding point on the graph of e to the x where the y-coordinate is s. We know that the slope of the tangent line to the graph of the natural log of x at s is 1 over s, since the derivative of the natural log of x is 1 over x. Now, the tangent line to the graph of e to the x at the point with y-coordinate s is the reflection of the tangent line to the graph of natural log of x at s about the line y equals x, and so the slopes of the two lines are reciprocals of each other. Thus, the slope of the tangent line to the graph of e to the x at the point with y-coordinate s is 1 over s, or s, but s equals e to the x-coordinate of that point. In other words, the slope of the tangent line at x e to the x is equal to e to the x. So the derivative of e to the x is e to the x. Now let's give a different, simpler derivation of that fact. We'll first write natural log of e to the x equals x, and then differentiate each side with respect to x. Using the chain rule on the left side and the fact that the derivative of the natural log of x is 1 over x gives us 1 over e to the x times the derivative of the inside function e to the x. On the right side, we have dx equals 1. So we just multiply by e to the x, and we have the derivative of e to the x with respect to x equals e to the x. So the base e exponential function is its own derivative. Now, combining that fact with the chain rule, we have that the derivative with respect to x of e to the u equals e to the u times du dx. The crucial thing to realize here is that e to the u is a composition, with u playing the role of the inside function. Now let's look at a few examples. First, let's compute the derivative of e to the minus x squared. Here we have e to the u with u equal to minus x squared, the inside function. So the derivative is e to the minus x squared times the derivative of minus x squared, which is minus 2x. So notice that we simply multiply the function by the derivative of the exponent. Now let's rewrite this as minus 2x times e to the minus x squared. Another example. The derivative with respect to x of x times e to the minus 2x. Here we'll use the product rule. The derivative of x is 1, so we have 1 times e to the minus 2x plus x times the derivative of e to the minus 2x. That is e to the minus 2x times the derivative of the exponent, which is minus 2. Now let's simplify this by factoring out an e to the minus 2x. We have 1 minus 2x times e to the minus 2x. Another example. The derivative with respect to x of 1 over 3 minus 2 times e to the minus x over 2. Now let's think about this as the derivative of the denominator raised to the minus 1 power. So by the power rule, the derivative of this outside function gives us minus 3 minus 2 times e to the minus x over 2 to the minus 2 power. Now we multiply by the derivative of the inside, which is going to be minus 2 times e to the minus x over 2 times the derivative of minus x over 2, which is minus 1/2. So now let's simplify. We'll have minus a fraction whose denominator is 3 minus 2 e to the minus x over 2 quantity squared, and whose numerator is equal to e to the minus x over 2. Integrals. Since the base e exponential function is its own derivative, it is also its own antiderivative. So the indefinite integral of e to the u du is e to the u plus c. For example, find the indefinite integral of e to the minus 2x dx. We can make the substitution u equals minus 2x, which gives us du equals minus 2 dx. And so the integral becomes the integral of e to the u times dx, which is minus 1/2 times du. So we have minus 1/2 e to the u plus c, which is minus 1/2 e to the minus 2x plus c. Now notice that the integrand here has the form of e to a constant times x. The result was 1 over that constant times the same function plus c. Notice that this is just the opposite of what happens when taking the derivative of e to a constant times x, when the result is the constant times the same function. So in this case, it's easy to simply write down the indefinite integral by inspection. In fact, the indefinite integral of e to the kx dx is equal to 1 over k times e to the kx plus c. Another example. The indefinite integral of 1 over the square root of x times e to the minus square root of x dx. Here we'll substitute for the exponent minus square root of x. We compute du, obtaining minus 1 over 2 times the square root of x times dx. So we have the integral of e to the u, and 1 over the square root of x times dx is equal to minus 2 du. So we have minus 2 times e to the u plus c, and now replacing u with minus the square root of x gives us minus 2 e to the minus square root of x plus c. Another example. the indefinite integral of e to the minus x divided by 2 plus 3 times e to the minus x dx. Here we'll substitute for the denominator. We'll let u equal 2 plus 3 times e to the minus x, which makes du equal minus 3 times e to the minus x dx. So our integral becomes the integral of 1 over u times e to the minus x dx, which is equal to minus 1/3 of du. So we have minus 1/3 of the natural log of the absolute value of u plus c. Now replacing u with 2 plus 3 e to the minus x gives us our final result. Notice that we don't need absolute values here, since the quantity inside the logarithm can never be negative. Limits. Since the number e is greater than 1, it's clear that the limit as x approaches infinity of e to the x is equal to plus infinity, and that the limit as x approaches minus infinity of e to the x is equal to 0. These limits describe the fact that the x-axis is a horizontal asymptote for the graph of e to the x in the negative direction, and there is no horizontal asymptote in the positive direction. The same limits are true for e to the kx for any k greater than 0. If we replace x with minus x, the graph is reflected about the y-axis, and the limits at plus and minus infinity switch. E to the minus kx with k positive approaches 0 as x approaches infinity, and infinity as x approaches minus infinity. It also turns out that the limit as x approaches infinity of x to the p times e to the minus kx is equal to 0 for any positive k and p. The graph of x to the p times e to the minus kx will generally look like this for positive x when k and p are positive. Notice here that the function is the product of a factor that goes to infinity and a factor that goes to 0. What's interesting is that the product x to the p times e to the minus kx will approach 0 as x approaches infinity, no matter how large p is and no matter how small k is. So the e to the minus kx factor always dominates. Let's look at a quick proof of this limit. First, let's rewrite x to the p times e to the minus kx by replacing x with the natural log of t. Note that t equals e to the x, and so t approaches infinity as x approaches infinity. Next, rewrite minus k times the natural log of t as the natural log of t to the minus k power, which is equal to t to the minus k, or 1 over t to the k. So we have natural log of t raised to the pth power over t to the kth power, which we can express as the pth power of the natural log of t divided by t to the k over p. Now, by a previously proven limit, the natural log of t divided by a positive power of t approaches 0 as t approaches infinity, and so we're done. Since x to the p times e to the minus kx approaches 0 as x goes to infinity, its reciprocal will approach infinity as x approaches infinity. That is, the limit as x goes to infinity of e to the kx divided by x to the p is equal to infinity for any positive k and p. In other words, no matter how small k is, e to the kx grows so much faster than any power of x as x goes to infinity that the quotient here approaches infinity. Example. Sketch the graph of the function f of x equals x squared times e to the minus x. First, let's compute f prime. By the product rule, we have 2x times e to the minus x plus x squared times the derivative of e to the minus x, which is e to the minus x times minus 1. Now let's simplify here by factoring out an x and also factoring out e to the minus x, leaving the third factor to be 2 minus x. So we can now take note of the fact that we've got two critical numbers, x equals 0 and x equals 2. Notice that the e to the minus x factor is never 0. When x is negative, it's easy to see that f prime of x is negative, and when x is between 0 and 2, f prime of x is positive. So we can say that the function f has a local minimum value at x equals 0, and that value is 0. At x equal to 2, the derivative changes from positive to negative, and so there's a local maximum at 2. That value is 4 divided by e squared. Now let's compute the second derivative. Before we do that, let's multiply out the first two factors of f prime so that we'll only have to do one application of the product rule. So f double prime is the derivative of the first factor, 2 minus 2x, times e to the minus x, plus 2x minus x squared times the derivative of e to the minus x, which is minus e to the minus x. Factoring out e to the minus x and simplifying gives us 2 minus 4x plus x squared, all times e to the minus x. So the graph of f will have inflection points at the two solutions of the quadratic equation x squared minus 4x plus 2 equals 0. By the quadratic formula, those two solutions are 4 plus and minus the square root of 16 minus 8 divided by 2, or 2 plus or minus root 2. Now let's take note of the fact that the limit as x goes to infinity of x squared times e to the minus x is 0, which tells us that the line y equals 0 is a horizontal asymptote. Now let's sketch the graph. We'll begin by plotting the point 0, 0, and recalling that the function has a local minimum there. Now the value at 2, where f has a local maximum, is 4 over e squared, which is a little bit less than 1/2. So we'll plot the point there and then indicate that we have a local maximum. The numbers 2 plus and minus the square root of 2, where inflections occur, are located here and here. And let's indicate that y equals 0 is a horizontal asymptote. For negative x, f of x is decreasing and is concave up, remaining concave up until x equals 2 minus the square root of 2. Then it continues to increase until x equals 2 while being concave down, and hits an inflection point at 2 plus root 2. Then for x greater than 2 plus root 2, f prime of x is negative, f double prime of x is positive. The function itself remains positive and approaches 0 as x goes to infinity. Other bases. The key to differentiation and integration of exponential functions with bases other than e is a simple way of converting such functions to base e. For a positive base b, b to the x can be rewritten first as e to the natural log of b to the x, and then by a property of logarithms that can be written as e to the x times natural log of b, which we already know how to differentiate. So the derivative of b to the x is the derivative of e to the x log b, which is e to the x times log b, times the derivative of the exponent, the constant natural log of b. Now we just re-express the first factor as b to the x. And since that tells us that b to the x is the derivative of b to the x divided by the natural log of b, we have that the indefinite integral of b to the x is b to the x times 1 over the natural log of b plus c. So no matter what the base is, we differentiate and integrate in essentially the same way as with e to the x, except we multiply by the constant factor natural log of b when differentiating, and we divide by natural log of b when integrating. Note that these formulas also cover the base e case, since the natural log of e is 1. Now let's look at a few examples. The derivative with respect to x of 2 to the x power is simply 2 to the x times the natural log of 2. The derivative with respect to x of 10 to the minus x over 3 equals 10 to the minus x over 3 times the natural log of 10 times the derivative of the exponent minus 1/3. So we have minus log 10 divided by 3 times 10 to the minus x over 3. Let's find the indefinite integral of 2 to the minus x dx. If we substitute u equals minus x, we have du equals minus dx, or dx equals minus du, so the integral becomes minus the integral of 2 to the u du. So this is going to be minus 1 over the natural log of 2 times 2 to the u plus c, or minus 1 over natural log of 2 times 2 to the minus x plus c. Logarithms. The key to dealing with other base logarithms is a basic conversion formula with which we can convert to the natural logarithm. That formula is log base b of x equals natural log of x divided by natural log of b. So the derivative of log base b of x with respect to x is equal to 1 over the natural log of b times 1 over x, or 1 over x times the natural log of b. Notice in particular that for the common log, or log base 10, we have the derivative with respect to x, common log of x, equals 1 over x times the natural log of 10.